So let's go ahead now and find expressions for the group and phase velocity. So we're going to have a wave that looks like this. We've got an envelope in red here and the ripples underneath. The ripples, sometimes known as the carrier frequency. So that's like the center frequency of the wave. And the envelope is some finite shape in space and also in frequency. And so the ripples in this case are going to have the wave vector kc. So it's like the frequency in space of the wave, the spatial frequency of the wave, and the shape of the envelope here is f of x. I want to find out how the red envelope moves. That's our main motivation here, is finding the group velocity, that's the speed of that red envelope. Now, I've written this function of x here as a complex exponential times f of x. Now, of course, by this we just mean the real part, so cosine times f of x, but it's easier to take the real part later and just use the complex exponential notation for now for the purposes of the calculation. So let's take the Fourier transform of this pulse. Let's take the Fourier transform of all of this. Now, the Fourier transform of this function of x is going to be capital F of k, but I have this phase term out the front here, and we can use the shift theorem to write this as a shifted Fourier transform, shifted by the amount kc. So this is the Fourier transform of our pulse up here, our pulse with the carrier frequency in it. Now this wave will travel through a medium with dispersion so that omega is a function of k. And we're going to assume the pulse has a narrow range of frequencies, or narrow enough so that around this value kc and this value omega c here, the slope of the dispersion relation is approximately constant. So this constant slope here applies for the range of the frequencies within our pulse. If our pulse has too many frequencies and leaves this range, and we can no longer assume this slope is linear, then this derivation that follows will not be valid. So if we do have an approximately constant slope, we can expand our dispersion relation to first order around the center frequency kc. So we get omega k is approximately equal to omega c, which is the center frequency here, plus the derivative d omega dk, which I'm going to identify here as Vg, some constant, and it's multiplied by k minus kc. So that's our linear expansion. And you may have already guessed that Vg is going to be our group velocity. If we write down the pulse propagation as an inverse transform over k, so this is recipe 1, we get this. So our function of x and t can be written as this inverse transform of our pulse in frequency space multiplied by the phase term here. Now the phase term here depends on the dispersion relation. We can use our first order expansion here and expand it like this. We can collect all of the terms here that do depend on k, because they'll be playing a role in the Fourier transform, and we take out all the terms here that do not depend on k. We have a term here kc, but that's a constant. These terms here are just phase factors that depend on kc, vg, omega, c, and time. This part here we can do the Fourier transform, because again this is something that's been shifted, and this is shifted in k, and this is a phase rotation over k. So we can take the Fourier transform. Got to do it a little bit carefully here, so we get all the shifts and the shifts in k and shifts in phase correct. But if we do it, we get this expression here. So this e to the I Vg kt gives us this delta function convolved with this phase shifted f of x shifted in kc. Evaluating this convolution will give us this expression. We get some cancellation here. This group velocity term here, Vg, cancels with this one over here. And finally we get this expression here. Taking the real part of this, what we get is that f of x of t has a cosine term out the front. This is our carrier frequency, our ripples, and then we have our envelope here. The envelope we can see is propagating along at a speed vg. That's our group velocity. The ripples underneath, the carrier frequency, well, they have a speed omega c divided by kc, and that will be our phase velocity. So this expression here encapsulates all the results that we're looking for. The envelope moves at the group velocity, which is vg. It's the derivative d omega dk at the value kc, and the speed of the ripples under the envelope, that is the speed of the carrier, is the phase velocity given by omega c divided by kc. Now if you're calculating how fast a wave moves from one place to another, which one should you use, phase velocity or group velocity? They're both speeds, they both represent the speed at which some part of the wave is moving, but which one do you use under which circumstances? Have a think about this question, and we'll come back to it and discuss it in a workshop.